All right, so today we're going to be doing some work with some word problems using exponential functions. So we've got three different kind of formulas or ways of doing these. The first is going to be exponential growth. Any time you're doing exponential growth, so we're going to use our same formula from yesterday, y is equal to ab to the x, where a is going to be my initial amount. B, which is the base of my my term that has the exponent, is going to be my growth factor. And my growth factor, underline it here, is going to be 1 plus the percent rate of change. And then the last thing, my exponent, is going to be the time that goes by. So the exponent is time. So with the first problem, since 2005, the amount of money spent at restaurants increased by 7%. In 2005, the initial amount was $36 billion. So if the trend continues, how much will the U.S. spend on restaurants in 2008? So my initial amount is going to be $360 billion. We're just going to leave it as 360 and put a B next to it for billion. My percent of increase it is increasing by 7% each year. So again, to turn a percentage into a decimal, I'm going to take the decimal point, which in this case is right here, and I'm going to move it 2 places to the left. So it'll become 0.07. And so again, my growth factor is always 1 plus my percentage, so it'll be 1.07. So that's going to be like my growth factor, my B in my formula, and then the last thing is going to be the time that passes. So from 2005 to 2018 is 13 years. So when I do this, I'll go y is equal to my initial, which is 360, times my growth rate, which is 1.07, growth factor, to the 13th power. And I can just plug that in as is in my calculator, go 360 times 1.07 to the 13th power. And I get y is equal to $867.5 billion on restaurants. Okay. With the next problem, same thing. Again, I always start it by finding out my 3 things I need: my initial amount, my percentage, and then my time. So my initial amount in this case, 285 cell phone subscribers in some little town. It's increasing by 75%. So 75%, which again, change it to a decimal, is 0.75. Add 1 to that, and I get 1.75. And then the time that goes by from 85 to 94 is 9 years. 85 to 94, 9 years. And so when I write this, I'm going to go y is equal to my initial amount, which is 285, times my growth factor, which is 1.75, to the power of 9. When I plug that in, 285 times 1.75 caret 9, I get that y is equal to 43,872 people. Again, I'm going to round it to the nearest whole number because I'm talking about people. It's 0.9, and so that would round my whole number up to the next number, which is 2. The next type of problem this will be exponential decay. This is sometimes a little more tricky. My A is still my initial amount. My B is now my decay factor, which when I do this, this is something we have to do in our calculator, is 1 minus the percent. So sometimes we subtract it in the wrong order, end up with a negative number somehow. It'll never be a negative number. It'll always be a number that's less than 1. And then my exponent is still the time that goes by. So in this problem, again, I'm still setting it up the same way. Initial amount, my percentage, and then the time that goes by. So I bought my truck in 2007 for $17,000. It's depreciating. Depreciate means decay, or it goes down. So it decays by 15% each year. So 15%, which is 0.15. And so again, I have to do 1 minus 0.15. Don't guess. Don't try to do it in your head. We mess it up more often than we get it right. So 1 minus 0.15 gives me 0.85, or 0.85. So that's my decay factor. My time that goes by, let's see, from 2007 to 2017 is 10 years. And so again, I'm just going to plug these values in. So y is equal to 17,000 times 0.85 to the 10th power. So 17,000 times 0.85 to the 10th power. So that gives me y is equal to $3,346, and it's 0.864. So I'm gonna go 86 cents. Keep it as it is. Again, I'm talking about money, so make sure I put $sign on it. So in 10 years, it depreciated, went from $17,000 to $3,300-ish. Flip over to the back. On the back, talking about enrollment at Wittenberg. So enrollment at Wittenberg is 1,910 in 2011. So my initial amount is 1,910. My percentage, again, it's decreasing by 9%, which is 0.09. Again, do minus 0.09. And I get 0.91 for my decay factor. And then the time goes by, so this is from 2011 to 2017. So that's going to be 6 years. And so when I do this again, I go y is equal to my initial amount, which is 1,910 times 0.91 to the 6th power. So plug it in just like that, and I get y is equal to 1,000, and I'm talking about people, so I'm going to round to the nearest whole number. It's 0.6, so I'm going to round it up to 1,085 people, or students, or whatever. And then the last one, compound interest. Compound interest is when you're investing money. Depending on how often it's compounded, most of the time it is compounded yearly. So that just means after each year that passes, they take the balance and apply the interest, and then you get a new balance. So it's like you're reinvesting your money each year that goes by, or however often it's compounded. So similar, but now we're just using kind of a different formula here. So P is going to be my initial amount. R is going to be my percent. N is going to be the number of times it's compounded. And then T is going to be the time in years. So when I do this, first problem, when your friend's born, parents deposited $2,000. So my initial amount is $2,000. My percentage is 4.5%, which again we're going to put into a decimal, which is 0.045. So we're going to go, let's see, N for the number of times it's compounded. If something's compounded quarterly means 4 times. And then the time that goes by is going to be 18 years. And so when I do this again, A is equal to my initial amount, which is 2,000. In the parentheses, I go 1 plus the rate divided, so 0.045 divided by the number of times it's compounded, which is 4. And then in my parentheses, I'm doing the number of times it's compounded times my years. So when you're doing this is the only one that's a little bit different. I can't just plug it in as is. I have to do the exponent first, or else it'll do it incorrectly for me. So 4 times 18 in your calculator gives you 72. So that's the only thing I need to simplify before I do anything else. So 72 for my exponent. And then when I plug it in, I can actually do it just like that. So let me jump over to my graphing calculator. So when I plug this in, again, I'm going to take my initial amount, which is 2,000, parentheses 1 plus my rate, which is 0.045, oopsie, divided by the number times it's compounded, which is 4. Close my parentheses and then take it to the 72nd power. Just like that. So that's the way I should plug it in. I don't need any additional parentheses or anything. Just like that is good. And so I get $4,475.53. So my answer for this ends up giving me $4,475.53. Then the last problem is we're going to take the previous problem, so the one that we just did above there, and instead of it being compounded quarterly, we're going to figure out what compounded monthly. So my initial amount is still that 2,000. My percentage is still going to be that 4.5%, which is 0.045. Number of times it's compounded is going to be 12. Again, if it's compounded monthly, there's 12 months in a year. And then the time is still going to be 18 years. And so when I plug this one in, I go still 2,000. Oops. And then in parentheses, 1 plus 0.045 over top of 12. And then in my exponent, I do 12 times 18. So again, I got to go 2,000, 1 plus 0.045 divided by 12. And then 12 times 18 gives me 216 in my exponent. So when I plug this in, 2,000 parentheses 1 plus 0.045 divided by 12, and then take it to the power of 216. And so I get $4,489.01. So compounded quarterly, compounded monthly. Compounded monthly gets me, what, $13.50 more or so. So not a huge difference there. Going to have to increase your initial amount or your rate if you're trying to make more money, not the time that it's compounded.